Genau. So we come to the topic we want to talk about today. It's nuclear energy, and it's a recent topic because just a few days ago, Castor Transport with 6 containers went through Bremen. Maybe you have heard about this. This were containers with radioactive waste coming from England, going through Bremen to Biblis. This is in the center of Germany in Hessen. Yeah, this is nuclear waste, which has to be it needs a place to stay for a very long time, but Germany doesn't have this place yet, and so it just goes to Biblis in this case. And Silke Westphal says to that she's from the group Castor Stoppen, Stop the Castor Transport, to transport nuclear waste from an unqualified place to another unqualified place is, independent of the pandemic situation, unnecessary and wrong. And why this is so, we have our guest here today, Bernhard Stoevesandt, and he will talk about nuclear energy and what we should know about it. Hello, Mr. Stoevesandt. Nice to have you here.
Yes,
I would
hello.
hand over to you now.
Okay, I tried to turn on my camera as well. I don't know. I hope this will work. And we still stay on. Okay. Yes, and I need to be presenter, exactly. Let's see, how did I get this again? Actions like this. Upload a presentation, I don't know. Maybe I can do this. And confirm. Yes. Okay. Thanks a lot. Okay, I will. It's say it this way. Like a few days ago, we had a discussion also at the students. There was this discussion also at the Students for the Future in Oldenburg on this, and well, my impression from this discussion was, okay, nuclear power in Germany, that has been a very long debate about it. But this long debate about it is like 10 years ago almost. And since then, not much has happened. So I will give you a short introduction to, in general, nuclear power and this discussion there. And I think that's the most important discussion, that is about how is it connected to climate change? And yes, so I'm not going too much into detail on these transports. Maybe it's a bit self-explanatory later why these transports are not really a good idea. So about myself, I'm a physicist. I work in renewable energies now, but originally, actually, I started to study physics because I was interested in nuclear energy, what it is about, and how it works, and also to be on a very stable base, and if I want to criticize it. So that was one of my motivations at the time, and nevertheless, I ended up in studying first more climate stuff, and then I ended up in wind physics, but that's a bit of a different story. So I will, oh no, this is wrong. Okay, I will give you a short thing. In English, actually, it's very easy. It's nuclear power. In Germany, there's a debate about is it gonna be Atomkraft or Kernkraft? And this has a long story behind that, because basically what is being done is that the cores of the nuclear of the atoms are being split, and therefore the atoms are being split. And so there are like forces within these atoms that have to be overcome. So the nuclear forces. And in Germany, it's the there's like the mixture. Some people say Atomkraft, so atom power. Some people say nuclear power. And the thing is behind that well, in Germany, you don't say it's a nuclear bomb, but it's an atom bomb. And it was a political decision in the end, then after the usage of the word atom bomb, to go to actually use the power, the well, civil way of extracting power from the same process, nuclear power, because it's supposed not to remind people so much of nuclear, of the bomb. So I will give you a short introduction into, well, maybe some time ago you had this in school, I don't know, about how this works. Generally, the material, everything in our environment is made of atoms. And each atom has a different chemical characteristic. And they also have different weights. The chemical characteristics depend on the protons within them. So they have different ingredients, these atoms, which are protons, electrons, and neutrons. And the protons and electrons basically are decisive for the characteristics of the chemistry of an atom, while protons and neutrons, since the electrons really don't weigh very much, these two are more for the atom weight. And the way it is written here is the upper number is the weight, and the lower number is basically the the electrical Ladung.
Charge.
Yeah, exactly. So within these within these atoms, there are like two main forces decisive for the process to describe here. One is the electromagnetic force. This is between negative charged electrons and the protons. These forces, they're not as strong as the other ones, but they have a longer reach. The other ones are the nuclear forces, and they are between the neutrons and the protons, and also between the protons and the protons, and so on, so between the nuclei. And they are very strong forces, but they only have a very short distance reach. So, this results in a situation where the protons between each others would repel each others due to the electromagnetic forces, but they're attracted by each others by the nuclear forces. And so most of the atoms wouldn't just exist if there wouldn't be also neutrons, which only have the nuclear forces. And the mixture of protons and neutrons then make up all the nuclei of the atoms. So they make it stable. So it depends on the right mixture between neutrons and protons. Okay. So there's only the only atom that exists with only a proton. That's it's hydrogen, and everything else, any type of other atom has different mixtures of neutrons and protons. Here I have to go for this. This results in the situation that a core of an atom, the more protons it has, the even more, so more than proportional, super proportional, more the neutrons it has to have. So it's in helium, for example, there's regularly, for a stable helium atom, there's four nuclei, so 2 protons, 2 neutrons, and further on the amount of neutrons get more and more and more, because otherwise the protons, the distance between the different nuclei increase, of course, if the atom gets bigger, but the nuclear forces are working only on such a small scale that the electromagnetic forces otherwise between the protons would be too big, so it needs more neutrons to neutralize that. And that results in a situation that, for example, here it is for iron and for uranium. And iron, for example, the amount of neutrons is 1.15 times more than the protons, while in uranium it's 1.58. So it's there are a lot more neutrons in that. And also, that's also something that's happening, is that if these nuclei gets too big, they have the tendency to fall apart. So basically, they're not stable anymore. And this is the case for all atoms that are heavier than lead. And this falling apart means they're unstable. That means they're radioactive. So there are different types of radioactivity. So all atoms that are heavier than lead are unstable. And for example, uranium, this one is the uranium-238 in the weight, emits then a core of helium, so 2 neutrons and 2 protons, to become thorium. And well, this is called alpha radiation. Okay. But then the thorium, since this is an equal amount of protons and neutrons, has even more proportional neutrons. And so that such atoms at some point have so many more neutrons that they're also unstable. So what then happens is that there might be some kind of change of a neutron, and it changes to be a proton by emitting an electron. And this emission of electrons is called beta rays, so beta radiation. And also there's going to be some emission of additional energy by electromagnetic radiation, which is called gamma rays. All this process of decay is something that is more or less it's like a statistical process, so it does not happen immediately, but it will happen sometimes over time, and this time depends on which type of isotope, which is called which type of atom with a certain weight I have. On this, it depends on how long this takes. So this is called half-time or half-life time, which says this is the time that half of these atoms have decayed to something else and have emitted this type of radiation. Okay, so it's this is like this lifetime thing is something that's very important in terms of the radioactivity, because it determines how long things are radiating. Now, if I want to split atoms, I need a core or an atom that's very heavy on one side, but it also needs to be rather unstable. And a very good isotope is the uranium-235. Now that's a different one than the one I showed I had here before. And if you put an additional neutron into this atom, and there's a way to do this, the nuclei of this atom will be unstable or become unstable and split. And by splitting, it will emit additional neutrons, and which can also split then additional uranium atoms, for example. And the nuclei will dissolve in two different parts usually, which have like a different size, and which part or which atom comes out of this is also something that is more or less a statistical process. So it's not really clear which exact atom this is. It's only more or less a distribution of all kinds of atoms. All this goes with the emission of a lot of energy, especially heat, since they are separating. All of this is separating, so there's going to be a lot of heat in that. And this heat is something that's trying to be used within nuclear power. Now, uranium itself in nature has a different type of mixtures of these isotopes. So typically, in a uranium in nature, we will have about 99.3% of this uranium-238, which is more stable than the 235 uranium, which is only 1.7% within that. However, most nuclear power reactors today try to use this uranium-235 because it's easier to split. Also, nuclear bombs, which use the same process basically, also use uranium-235 if they use uranium. So the basic process there in the bombs and the nuclear reactors is the same, only that in the nuclear reactors, it's tried to control this process. Now, how does this work? Basically, we have the uranium is mainly it's put into sticks, like long sticks with uranium pellets, and these are put into a pressurized well, it's like a heating chamber. I don't know what the word for that is. It's like a big pressurized water container where the process itself is happening. Well, since the process of the splitting of the atom depends on the neutrons, there's also some sticks in there that can absorb neutrons, and by that the whole process is tried to control. So it's not the correct word. the sticks with the uranium basically contain most of the time, since if it's regular water for cooling, 3% or 4% of uranium-235. And this heated up water by the process of the splitting then is used to run an engine, to a generator to produce the electricity. Water is cooled down, and the difference between the temperature of the hot and cool water is basically what drives the energy production. Everything in that usually is run under high pressure. So depending on the type of reactor, the pressure within that is something like at least between 100 and 250 bar atmosphere. So that's very under very high pressure, because the high pressure allows a higher temperature difference there. Theoretically, all the of the split material, so of the uranium, so afterwards the uranium has been split, all the atoms that came out of that are lighter. They do have too many neutrons within the core because the uranium had proportionally more neutrons, so they are also highly radioactive, but everything's supposed to stay within the sticks within this reactor. So ideally, afterwards, mainly the sticks should be radioactive, and all the materials should be in there and should be replaceable. This is, however, often not the case. A very typical thing is that they tear up, and then the whole water is also contaminated. And well, typically after running such a reactor, a lot of this inner circle, everything that has been in connection there, is also radioactive. Now, to get to that, this is not the only part of nuclear power, of course. There is also a lot of processing before and afterwards. And these also have to be regarded. And at each of these processes, there are radioactive wastes appearing that somehow have to be dealt with. The first part is the extraction of uranium. So basically, this is a global thing. Uranium, is something that is actually pretty much in the ground everywhere. So if you would go out and you would try to look for uranium somewhere in the ground here in Bremen, wherever around, you would also find that it's not that highly enriched, but there would be uranium. And there has been uranium mining in Germany too. But currently it's mainly done in more in indigenous regions, which are more remote, and where, well, people don't have so much of the same. It's more like poor people's regions, and that makes people more happy about, you know, that there is some kind of work, but it has some big disadvantages apart from, I mean, you know, this is a strip mine. It's in Namibia, which is like it looks like many strip mines, has a lot of impact on the environment, and one of the impacts is also that the while doing that, there's also a lot of uranium and other particles coming from the uranium dust in the area. And this is one reason, for example, oops, sorry. Here, for example, this is again in Australia, for example, where there's uranium mining in the Aborigine regions. And after that, after the mining process, of course, this has to be processed. So to finally get the real pure uranium out of this. In Germany, this has been done in a bigger scale in former East Germany, which was like the fourth biggest uranium mine before in the world. And also in West Germany, also in southern Germany. But there it was stopped after there was, I mean, it got a bit too expensive in a way, because not only because the wages are expensive, but also there was a high rate of lung cancer. And this is very typical in the areas of uranium mining. You do have a high rate of lung cancer because of this dust of uranium, which is radioactive, and people breathe this in, and then you have this, well, radioactivity basically from the inside of your body. And this is very, it's the most dangerous type of radioactivity if you have it inside your body. And this is, basically in Germany has been stopped. After it has been stopped, this uranium mining in especially East Germany, they had to, refurbish the area again, and they, the German state spent about 5.5 billion euro only to do this, to somehow repair and clean all this up afterwards. this whole thing, the whole process of cleaning this up costs even more, but this was mainly being paid by German taxpayers. So, and this is not going into the electricity bill, of course. So this is the part of uranium mining, which is kind of, well, like many mining processes, bad, but it has the side effect of this radioactivity. After that, after you've won the uranium, you cannot use it because you need somehow more uranium-235 within your probe afterwards to run it in the reactor. So after that, there's an enrichment process of the uranium-235. So in power plants, for example, you need a 3 to 4% of that. And so the uranium-238 has to be decreased. And this is done by, there are different processes how you can do it. Most typical ones are centrifuges. So basically you whirl the atoms as a gas around very quickly, and then the heavier ones move outwards, and you suck out the inner ones, which are supposed to be lighter, and then you do it over and over again. So this is like a picture of that. So you have many of these, one after another, again and again and again, and after a while, you have a higher percentage of the lighter uranium within your probe. Basically, this process is the same for if you go for nuclear bombs. For nuclear bombs, you need some uranium-235, which is like enriched to a 95%, which is a lot more than in power plants. But basically, the process is exactly the same. And if you have enough of this type of uranium in this high degree of enrichment, then it's actually very easy to build a bomb. And this is also the reason why there is so much excitement about that Iran actually has the technology to do this enrichment, because with that technology, it is only a process of, you know, how many of these centrifuges you put after another to build a bomb. I mean, there is still, you have to do some more work on that, but basically it only depends then on how much of this uranium you are able to put together in a very small time period to start the process of this explosion. So there is a very close linkage between the uranium enrichment and the military usage, and you need the enrichment for running nuclear power. And this very close link between nuclear power and nuclear bombs is actually also something that motivates states to go for nuclear power, because, well, nuclear bombs are, of course, a very powerful weapon. And for example, the UK, they have, I mean, I will come to that later, they're planning nuclear power plants because they say, we are nuclear power. We want to stay to be in nuclear power. And we need the people who are able to run this technology, and therefore we need nuclear power plants. They're very open with that. Oops. So then we have to run nuclear power plants. Ideally, everything runs smoothly, and well, the nuclear waste, so the split up atoms, stay within these sticks, and they heat up. This process afterwards, also, since all the material inside is after that heavily radioactive, very radioactive, and this still produces further heat for over a very long period, and that is why also after most of the uranium has been used for the reactor, for running the reactor, so basically there's not enough uranium anymore to run it. then they have to replace these sticks, and the only thing they can do with that is then to put it into a cooling pond afterwards, because only with this cooling pond, they're able to keep the sticks as a whole. Otherwise, everything would melt away. And this is, of course, a problem, because you have something there that has to be cooled for years before you can do anything with it. And if something goes wrong somewhere in this process, then you have this, this is a picture of Fukushima down there. You have a process that happens like it happened there, because there basically the cooling failed after the earthquake, and then, well, there were 4 power plants, and then some of them it was basically the failure was within the reactor itself, but some of them weren't running at the time, and there the cooling led to basically that the cooling ponds were also melting. So what also happens, and just by regularly running this, is that these sticks somehow tear up, and then radioactivity goes to the outside. I mean, the mixture and there of elements is all kinds of elements. Some of them are solid, some of them are liquid, some of them are gases, and the gases usually are emitted. That's why they have like a chimney here to emit radioactive gases in a further area around. But this, in Germany at least, there was a lot of studies on that, and they could prove that around all the nuclear power plants was sometimes in the 2000s, I don't know exactly the year when they published this, they could prove that all around the nuclear power plants, the rate of cancer was higher than it usually should have been. Such worst case scenarios, well, there was a minister of science at the time, 1989, who said, well, the probability that this happens would be every 33,000 years of running such a power plant. Okay, for one power plant, you could say, okay, well, this is supposed to be running for 30 years, that's no problem. But if you start to build like 500 of them, as right now there are like 400 running worldwide, then this probability decreases, and it decreases quite a lot, because, well, if it's only every 33,000 years of running such a thing, then all these power plants together, of course, have a higher probability that at least at one of them, something's going to happen. And, well, we had this now, at least, well, we almost had it in Harrisburg, or there was something like that happening in the US. We had it in Russia and in Japan. Yeah. Well, it's basically the point of that is that if nothing happens and you take one of these sticks out of the nuclear power plant, out of the cooling pond. So it has been in the cooling pond for 3 years. You take it out, you put it onto a field, and you yourself, you get onto a motorbike, and you would try to drive by at 100 kilometers per hour in 100-meter distance. You would not even be at the height, at the 100-meter distance of this one stick, because you would be dead by then. So it's like extremely deadly, the radioactivity within this. So, and after that, well, you have a lot of waste, and this is radioactive. So, yeah, and there is the question of what to do with this waste. And basically, currently, nobody knows exactly what is a good solution. Down here in red, there are some, there's like the half-life time of different types of radioactive atoms in there. There's, for example, plutonium, which is appearing in there, which has a half-life time of 24,000 years. And neptunium, then it's like 2 million years. Of course, there's not so much of it. It's not that, I mean, the longer the lifetime, the lower the radioactivity. Nevertheless, it's still radioactive. So in Germany right now, they estimate that, well, the nuclear waste should be stored away at least 1 million years. And 1 million years is, in terms of technology, it's a very long time. And we have a problem with that, because to predict that some place, somewhere on this world, will be able to store something away from life around for 1 million years is very, very hard. And they tried to do that. I mean, there were some ideas in the beginning. They started to put it in Germany. They put it into salt, and they did a try of that. That's the upper picture. Basically, there was a salt mine, and they dumped a lot of not so highly radioactive waste, but was kind of mixture in that. And now they found out, okay, there's water running in, and they expect that within the next 50 years, the water running in will also be running out of this former salt mine, and this would contaminate the groundwater, and this also is predicted to come up somewhere on the surface sometime again. So they're trying to evacuate this now. This costs, again, some billion euros. Yeah, basically also paid by the German government. Yeah, later on they tried to build another one of these salt pits in Gorleben. Now they found out it's not the ideal place, and now this is being rediscussed. But also this was a big project for €1 billion, something like that. So currently Germany has not a real place for that. Other countries claim they have it. But the question if the nuclear waste will seriously stay there for like 1 million years is a very hard to answer question. And the reason now for this nuclear transport, to maybe you wonder why this happened, the reason for them to happen was actually that the nuclear power plants were only allowed to run if they could prove that they have a place to store the nuclear the nuclear waste. And the way to prove that, or one way to prove that, was to make a contract with a refinement factory in England or in France, where they extract non-used uranium and plutonium from this waste, which then could be enriched again and maybe put into used as new nuclear fuel. And nevertheless, the waste itself is not being reduced by that process. And still, the waste itself was then in France and England and was stored there for 20 years. The contract was for 20 years. And this was used as a as a proof for that they are having a concept for the waste. And with that proof of a concept, they were allowed to run the nuclear power plants. Now the 20 years are over, and so this waste is supposed to come back. And and this is of course an issue, because they still don't have any place where to store this waste. And now the issue with that is now that as long as there's not a good place to store it, each of these transports are of course kind of risky, because whatever is in there, I mean, it's not just one of these sticks in there, but many of them. That's why these, the Castor is called cased for storage and transportation of radioactive material. It's like very special type of container, which is able to cool these things, to absorb a lot of the radioactivity, and supposed to stay closed for at least a lot of issues. But if they have an issue, and these transports are of course a risky issue, then it is a problem. So basically, a lot of people say better not do any transports as long as it's not clear where this waste goes. Nevertheless, nuclear energy is supposed to be free of fossil energy. And this could be good for the climate. That's what some people say. And in general, that's true. There's no CO2 emission directly by the power plant. Of course, there is currently CO2 emission by all this processing of the uranium, because that needs a lot of energy. But of course, in general, it's a lot less than just directly burning fossil fuels. Also, there's like within this splitting the atoms, there's also some like a gas evolving, like krypton, which is a gas which also has some climate potential, but in general that's not very big. So why not say, okay, nuclear powers might not be that nice, but compared to what climate change means, it's just maybe an alternative. And to answer this question, it's important to understand how this actually energy production work. Energy production is basically, there is like a daily cycle. So during daytime, people use more energy. During nighttime, it's less. And so it's not constant. Nuclear power plants, because they this process of splitting up the atoms and this radiation of these atoms afterwards is like a constant thing that's always heating. They cannot be just turned on and off. Actually, to turn on and off a nuclear power plant usually needs something for at least 4 days, and still needs cooling afterwards. And therefore, nuclear power plants run constantly at the same, more or less the same type of power. And you can see this. This is the red line down here. That's the nuclear power in Germany. This is like the German electricity generation and of this week. On the other side, we have well, solar power and wind power, which have a strong fluctuation depending on the amount of wind or sun. And well, this, of course, if we have more wind power or more solar power, like currently it's like this, that there's still the well, the coal and gas power in between here. But we actually have sometimes the situation that there's even more renewable energy in the grid. And this, since the nuclear power cannot just be turned off like that, this leads to basically that renewable energies are being turned off. So nuclear power and other renewable energies are not a very good combination. Sorry. But the main problem we have actually is the cost. Nuclear power is, because of all these safety issues you have with it, it's extremely expensive. In Europe, like in, especially like in, there's like different projects on where countries decided to build nuclear power plants. One was Finland, in Olkiluoto, In 2005, they started to build a reactor in France. They started to build one in Flamanville in 2007. And they're supposed to be ready to be running in 2022 or in France in 2023. So it took them more than 15 years to build one of these reactors. In general, originally, they were supposed to cost 3 or 4 billion euros. Today, it's like something like 9 or 12 billion. Yeah, but like they have a capacity of 1.6 gigawatts of electricity. In England, they want to build 2 reactors at a place called Hinkley Point, so that would be even double the amount of energy. They started off in 2017, and they expected to cost about 22 billion pounds. Compared to that, like wind power today costs about, like if you build like a 4 megawatt turbine, it costs about 3 million euros. So even if they don't, the wind energy doesn't produce all the time this amount of electricity because, well, it depends on the wind, of course. Still, the cost would be like something like 4.8 billion euros if you build like 4 times as much capacity with wind energy, which would be about the same amount of electricity. So in general, in England, for example, they say they guarantee the price for electricity of 92.5 pounds per megawatt hour at Hinkley Point, while offshore wind gets 57.5 pounds. So it's a lot more expensive to build, to pay this this electricity by this nuclear power plant. And the point is of that we will need a lot more money to be invested into the energy system, because we will have to replace all the other power plants. And this would lead to investments of at least 8 billion euros only in renewable energies if we do it as planned by our government currently, which is, in my opinion, not enough. This is a graph like this. The second column from the second column from the left is like the plan of the German government. The right-hand studies are more scenarios for climate neutrality for 2050, and these could there are even more scenarios which would this is from the study of the Wuppertal Institute, which say, okay, we would need rather on the right-hand side these scenarios here for climate neutrality. But if we take these scenarios here, we could see that we need even more than that in investments into per year into renewable energies. And we would even need more investments if we want to go for climate neutrality at 2035 or even 2050. For example, the study of Agora Energiewende, they say we will need probably about 70 billion euros per year in investments to reach this climate neutrality 2050. And then if we go into that and say, we just spent 1.5 times more money because we want to do nuclear power, then this hurts, because we have to spend already so much money in this change that in the end, such a higher investment into some technology, which is still risky and a problem, would most likely block the transition that we need to do. And this is the problem we would get in if we go for nuclear power. Now we have still 6 further running nuclear power plants, and so why not just use them further on, because they are already there, so they don't have to be built and so on. So we could say, let's run them a bit further. The problem with that is all of these power plants have been built before 1990. And in terms of technology, I mean, I don't know how old you are, but I know my computer I had in the 1980s. And this is the technology originally built into these power plants. Of course, they refurbished a bit and did a little bit more onto that, but in general, the basic construction concept was based on something of the 1980s. So it's really, really old, and a lot of the system within these power plants is really, really old. And since in 2000 there was the first call for, okay, we're gonna move out of nuclear energy, also the companies did not really invest so much more into these nuclear power plants to get them on the newest point of technology. The further problem is that you need people to run this, and therefore you need to educate people to run this. And I mean, would you study some kind of a field where you know, okay, basically the government of that country has already announced they will move out of it, and so most likely there will not be anybody hired anymore. So currently, I think there's overall Germany, I think about 30 people studying something in this field. This is not very much. So there's not even enough people to run them in the future. And they would have to go for well, new legalization of that, which is of course a more or less political issue. So theoretically, it would be possible to run them further, but there would be a lot of investments necessary to run them further, and they would need additional people to run this further. And this is the point where actually the operating companies say, well, currently we don't want that because it would be too costly for us to just do it. So if they should be motivated to that, then they would probably say, okay, well, the taxpayers should pay again. And here again, we go this way that, you know, that nuclear energy there is very expensive. And so the problem with running these old nuclear power plants for a longer period of time is again a cost problem. Of course, it's a political thing, and you could say, yeah, we're gonna pay no matter what. But since the transition of going for a climate neutral future is going to be expensive, and anyways, I mean, paying more is really something that needs to be discussed. So basically, this whole thing is about theoretically, nuclear power could be climate neutral, but it contains itself a lot of additional problems, and these additional problems will be a load on like the current and the future generations. And future, if I talk of future generations, will be a long, long time. Well, it's a technology. Basically, it keeps up the ideas of how to deal with nature, as we have done this before. So basically, the human being can go into nature and change it as human being like, and we don't have to think about what happens with that. And this is it's a question of we want to stay like that in the times of thinking. Nuclear power is expensive, and if we would use nuclear power to go for a climate neutral age or something, this would be well, lead to, at least it would make it a lot more expensive and would therefore also delay this transition. Theoretically, it's possible, nevertheless, to run these the nuclear power plants further on. However, at some point they need to be strongly renovated, and this costs a lot of money. And for example, to make this clear, I mean, costing a lot of money, the company in France, I mean, France runs a lot of nuclear power plants, and the company with the highest debt in France is this company running these nuclear power plants. And it's basically only alive because the government, the French government, subsidizes this company. That's it from my side. Please ask questions. I can talk a lot about this. Thanks a lot.
Okay, thank you very much. Yes, other questions? You can ask them in the chat and I can read them out loud, or you can unmute also. And in German, Sie können auch auf Deutsch Fragen stellen, wenn Sie möchten. Das wäre auch möglich.
Erstmal danke für diesen schönen Vortrag. Ich hätte allerdings eine Frage, und zwar, ja, ich war nie ein Fan von Nuklearenergie oder Atomkraft, aber wir haben nun mal diesen Atommüll jetzt, und ja, unsere Generation hat ihn wahrscheinlich auch nicht nach Sellafield geschickt, aber ganz ehrlich, wenn die Briten zu uns ihren Atommüll geschickt hätten und jetzt mit dem Abkommen, ihr nehmt ihn auch wieder zurück in 20 Jahren. Und jetzt würden wir sagen, würden die Briten zu uns sagen, nee, den nehmen wir nicht wieder zurück, wir lassen ihn bei euch. Den würden wir auch einen Vogel zeigen, oder?
Yeah. I will translate. Okay, the question is basically that, well, the nuclear waste that is right now in Britain has been brought there with the promise that it's going to be brought back as well. And of course, the British people would also, I mean, if we would do it the other way around, we also would like to get rid of this waste again. And this is of course true, and it's of course clear that this waste has to come back. The issue is, however, and this is actually consensus between all these groups working on that, that all types of non-necessary transport should be avoided. And so if this waste goes back, it should be clear where it's going to. And this is currently not the case. So basically, if the moving these things only if it's really necessary, and if it's really there is a concept behind that. And currently the concept is, there's not a real concept behind that. It's more or less, okay, they have to go back because, well, the UK is moving out of the EU, and they're trying to get this at least back as much as possible now, because it's there's a legal issue with that. But the British, well, anti-nuclear activists also say, hey, if they stay here a bit more, it doesn't really matter much, because of course you have to take back the waste. We don't want it, but it's a question of, that's more a question of time when. Sorry, there's a lot of questions. Sorry.
Yes. Soll ich das noch übersetzen oder ist okay? Auf Deutsch. Okay. So there are a lot of questions in the chat. I will start with Richard's question. What do you think about TerraPower's traveling waste reactor, which could stretch the reserves around 60 times, hence less atomic waste?
Yeah, this is, I mean, the thing is, yeah, it's not there. And it most likely will not help because because it's not there. And in the end, I mean, there are a few concepts like that. And the issue is, you know, in terms, if we speak of climate change, we have to think of, you know, when it's a question of time, you know, when we'll be ready, we will be ready to go for climate neutrality. And if we have to wait for such a concept for 10 more years to be really commercially available, and then start building this and then do the transition, we are already too late. And that's why it's such, you know, it's, of course, people are thinking about this. Nevertheless, these concepts are also, and that's the second part, all of these concepts will be most likely, because of the big technology issues that are involved in that, they will be too expensive compared, for example, to renewable energies. And in that way, they're in a way not compatible. Renewable energies now are just, they've become really, really cheap.
Okay. Melanie asks if you can describe the slide with the coasts again.
What with the coasts?
The costs.
The costs, yes. This one, yeah. Or which this one? Yeah. Oh, if I can explain it a bit more. Okay. Well, these numbers are here are like the currently estimated costs. So they don't know yet because it's not done yet completely. And some people say it might even be more expensive. But basically, the cost increased. Now the point of how much wind energy costs. This is really a question. It's very hard to compare because well, nuclear power runs all the time, day and night, and well, then they turn it off for about 3 to 4 weeks in a year to do some refurbishing and replacement of the uranium, and otherwise it's running, or it could be running. Sometimes it's not, but it depends a bit. But in general, we could say it will be running and producing exactly this amount of energy. Well, wind energy depends only on the wind. And currently, the capacity factors of the current turbines is that they, in average, produce 1/4 of the potential energy they can produce. So, a 4 megawatt turbine onshore in Germany currently produces about 1 megawatt in average. So we have to put 4 times as many there to produce the same amount of energy, and that's why I come up here. So we have to install then 6,400 megawatts in terms of wind energy to produce the same amount of energy as a nuclear power plant. And then I come up with 4.8 billion euros. This is a rather conservative estimate, because, like, for example, offshore wind turbines have a higher capacity factor, so you don't have to install so many. We will have other types of turbines that have a higher capacity factor also onshore soon. And well, the price for wind energy is still, well, could be going down, but this is currently prevented by the German law system in a way. It could be, I think it could be a lot cheaper, but anyways. But so a good estimate is then, of course, like in Britain, they still have this guaranteed prices for the produced electricity. And so this is for the nuclear power plant. They have this guaranteed price for 30 years. They get this 92.5 pounds per megawatt hour, which is like 9.2 cent. What would that penny they have per kilowatt hour? Okay, while wind energy is at like offshore wind energy, which is still more expensive than onshore wind energy, gets 57.5 pounds. So it's yeah, the nuclear energy will be more than 1.5 times more expensive in terms of energy than offshore wind.
Okay, the next question is about renewable energies, and for renewable energies we need storage capacity. That is often be claimed to be a problem. Can you say something about that?
Yes, currently this is or it could be a problem. Actually, it's less a problem than everybody expected. Like 10 years ago, if you would have asked most of the people, hey, would it be possible to have like 50% renewable energies within the grid? And everybody would have said, no way. Now we have this, and it isn't a problem. But currently, since the electricity it's only working by itself, it would be, if we increase further, this would be a problem. In the future, this will be less of a problem because we will have more of an interconnection between different types of energy. So we will use the renewable energy, electricity, for example, to produce hydrogen. And this can be used as a storage, for example, because the hydrogen can then be reused to produce electricity. Also, the electricity will be used for heating a lot more. And we need heating by electricity because this can be produced climate neutral way, and therefore a lot of the basically the way it works now is that we build up a lot more renewable energy, so that even if we have few wind, this few wind will be still enough to have the electricity grid running. But then we have a lot of cases when we have an excessive amount of electrical energy. But this can then be stored within the heating systems. Because if you have a heating system, and usually this, what's the English word for this? So if you have like a heating system that's not just for one house or so, but for like a whole area, for example, and this is being built up more and more, that like whole areas are being heated, then it doesn't really matter if your water for your heating within that is maybe 1 or 2 degrees warmer than usually, because you had too much electricity in the grid and you just heat it up a little bit more. So basically, the type of energy production will change by this new type of usage of energy a lot. And this will make the storage of electricity in the future a lot simpler. Even on large scale and on very large scales.
Okay, thank you. Then a question about the waste, the nuclear waste.
Yes.
Would it be a possibility to split the burning elements further up and store them all over Germany or the world?
Oh, well, we did this as a fun thing, to give everybody like a little box saying, hey, this is your share of your nuclear waste. No, it's seriously extremely dangerous. The plutonium, only milligrams of plutonium are deadly for you. So this is not anything you want to split up and you want to hand out to the people. No way. This it's good to somehow put it somewhere where it's really out of reach. And I mean, there are not so many places probably in the world where this can be done. And it's not a good idea to split this up. I mean, it's still a danger. And it will be a danger for the next hundreds of thousands of years. I mean, the of plutonium, the half-life time is 24,000 years. So, I mean, even in what's that? Well, like 100,000 years, you still have like 1/8 of the amount of you have now.
Okay, there was a question if we upload the presentation. Yes, we recorded this presentation and we will upload it on YouTube. And the next question, I heard that it is hard to dispose wind turbines due to certain metals. Is that true?
Well, no, it's not due to the certain metals. Metals will be. Yesterday I heard we had a scientist for future meeting, and we had a presentation on resources and resource material, and basically everything within all the metals within wind turbines in the future will need to be recycled. And everything has to have this cradle to cradle concept in that it's supposed to be recycled. Currently, the main problem of recycling in wind turbines are the blades, which are made of glass fiber or a composite material, which is like glass fiber with epoxy and then sometimes carbon fiber in that. And this is harder to reuse because basically everything's glued together. And but there are also concepts to work on this now. So like in wind turbines, where the metal is not a problem, this will be recycled. You can recycle all the metal, and it should be recycled. But the blades are currently more the issue, and this is, well, it's well, the way to do this right now is not so optimal because the easiest way to get rid of them is currently to burn this, because all the glue, it burns. That's not so nice.
Okay, isn't nuclear power a CO2 neutral alternative for the Dunkelflauten, times when there is no wind or sun?
Yeah, that's a good one. I love Dunkelflaute because well, we basically we calculated this once because there was once in the physics journal also this question: hey, if we have 6 weeks of no sun, no wind, and you know, what's going to happen? Or I think, was it 6 weeks? I think they were like 6 weeks and so on. And then we what we did was we looked at. There is like it's called strategic storage for gas currently, and well, of course, like currently for natural gas, but in the future this could also be used for example, hydrogen or artificial gases made out of CO2 and hydrogen. And if we use this type of storage, then would be we could even go for 3 months with the stored gases made from either biogas or by hydrogen within these storages. We could go for the whole electricity system for at least 3 months now. And this is so it is the Dunkelflaute is not really the problems. I mean, it would be something we didn't do this yet to see, you know, how often do we actually have such situations. We have such a situation sometimes for a few days currently, but to have this like for something like 6 weeks would be very interesting. How often this happened during the last years. But this is very, very. I'm not saying it's impossible, but but even 6 weeks would be durable with going by hydrogen or biogas. So we wouldn't need nuclear power for that.
Okay, Leah's question is answered, I guess. So Caroline's question: what can we do to minimize the loss of energy when we save it? When we
That's a good question, because well, hydrogen, for example, is usually, like currently, we only use 60% of the energy if we produce hydrogen. So the basic idea currently is to use as much electricity in terms of electricity directly as electricity. If we have to storage, then there are different concepts of storages. Nevertheless, we will lose always energy in that, and that's why the aim is, of course, to use as few as possible. For example, to use this as a heating in the heating system, this is actually a rather smart way of doing it, because it would be like a direct usage of the electrical energy, and you can insulate heating systems very, very well, so you can keep the heat for a rather long period of time. But in general, this is, of course, a topic which, because like if you go, for example, there's always this discussion, you know, how much hydrogen should we use and how much electricity should we go for hydrogen cars, or should we go for electric cars? And well, all the people in this energy system debate, they all say, hey, we should go for electrical cars, because then we can directly use the electrical energy and we don't have to lose energy by splitting water to hydrogen, so to do hydrolysis. But it's a good question, because well, there is, of course, more technology to be developed, but yeah, what can we do there? I mean, it's a question of there can be things done, but we will always have loss, and we should keep it small.
Okay, thank you. I don't see further question. Oh, I see a further question. From Richard: is the calculation of the no wind, no sun times public? Can you share the report?
Oh, the one that we did, no, we did it for ourselves a bit. It was basically an answer to this article in the physics, it was not an article, it was a letter to the editors of the physics journal. But I can give you the well, what I could do is I could provide the calculation, what we did, the base, how we calculated that. I have it somewhere. I can take it out and do it. Basically, we used took a state-of-the-art power plant as a gas power plant as it is right now, calculated the volume of the strategic storage, and how much energy, how long this power plant could be run, with what kind of energy production. And from that, we had like an overall estimation of how much energy can be produced by the strategic storage as it is right now. It's like a huge amount of gas that can be stored currently.
Okay, but now I don't see any more questions. Are there more questions? You can also unmute. Otherwise, I would suggest that we could come to an end. Okay. Yeah, thank you very much